One more problem for this section. In this problem, we're going to try to build some intuition for the idea of normal subgroup by classifying all normal subgroups of S3 and D4. And we're going to see how we do on time here because, well, as we're going to see, the bigger the group is, the more subgroups there are, and the more possible ways we could look for normal subgroups. And so maybe we'll do S3 and we'll see how far we get into D4 in a reasonable amount of time. And I'll let you guys finish the classification. Now, worth pointing out is that by classify, what I mean here is like find them all and kind of sort them into bins for how they come about. So the strategy that comes to mind when I see this is to start by finding just subgroups, just all the subgroups I can, and then seeing which ones are normal. So in S3, sorry, I'm not sure why that happened. In S3, what kind of subgroups do we have? Well, there are cyclic subgroups in subgroups generated by one element, and then there are subgroups generated by two elements. And it turns out that that's all that's possible in terms of um, I don't know what you call this, the number of generators of subgroups. I don't think that has a name. The reason that this is all that's possible is because in S3, every transposition is either the identity element or a transposition or a 3-cycle. And if I wanted to pick two non-trivial elements, I could pick two transpositions, which would always give me a 3-cycle. And if that's not clear, we'll return to it in a moment. I could pick a 3-cycle and a transposition, which we know from our discussion of the structure of S3 is already the whole group. And it turns out that there really aren't two different 3-cycles. There's just rotate one way and rotate backwards. And those are powers of each other. So that doesn't get you anything new. And so these are the two possibilities. So let's try to enumerate then what are the cyclic subgroups. Well, we have subgroups generated by transpositions. So that's these guys, each of which is abstractly isomorphic to a Z mod 2Z, but none of these are normal. Why? The reason is because to be normal, to have a normal subgroup in general, means that if you have any H in your normal subgroup, then XH inverse is also in H for any X. But we know what conjugation does to a cycle of any type in S3. It permutes the underlying symbol. Well, if I permute the underlying symbols that make up the permutation, I'm not going to land back on myself because there just aren't enough elements in S3 to possibly, I mean, it's not even that there aren't enough elements because I could always try to conjugate by something that contains one of these guys. Like I could conjugate 1, 2 by 2, 3. And that would change the 2 into a 3 and thus land me outside the group generated by just 1, 2. Same logic works for all of these guys. So no shot there. Other cyclic subgroups would include things of product of transpositions or a 3-cycle. Now it turns out that a 3-cycle, like 1, 2, 3, actually is a product of transpositions. And so I only have to look at just one of these guys. And so we could consider the group generated by 1, 2, 3. This one is normal. And there's two ways that I can think about seeing this. What are the two ways? The first is by direct calculation. You could go and try to conjugate by different elements. And that's not so bad. So let me give you a sense of what that might look like. If I conjugate this by another 3-cycle, we just talked about how I could think of 1, 3, 2 as this thing squared. And so all these things commute with themselves. And so we would just be rearranging powers of this thing, which of course would land you back in the subgroup generated by that thing. So that part would be okay. On the other hand, if I instead tried to conjugate by a transposition, well, let's see what happens. Any transposition, like let's do the first one just so you can have the idea. We're going to swap 1 and 2, right? 1, 2 inverse equals 1, 2. This switches 1 and 2 inside and gets us to 2, 1, 3, which in turn is equal to 1, 3, 2 by taking this and putting it at the end because it's a cycle. And 1, 3, 2 equals 1, 2, 3 squared. So we land back in the group generated by this thing. And you can convince yourself by just checking what happens with the others that this always is more or less the case. Because there's no way to be a disjoint cycle from 1, 2, 3. So when you do one of these non-trivial transpositions, you just end up with a different rotation. And so we're normal. The other way that this could go, if you didn't want to like check element by element, is to refer to the following fact, which I actually don't think we've proven yet, but it's sufficiently important that I feel like you should know about it. So I'm going to put it into your head right now, which is an index 2 subgroup is always normal. And we recall that index, I don't know if we talked about this in the videos. Now that I'm thinking about it, I don't think we did, but I'm pretty sure it's in Pinter. This is the number of cosets your subgroup has. So in other words, if G over H in order equals 2, H is normal automatically. And that's what happens here. Again, two ways I can think about seeing it. The first is that the order of S3 is 6, and the rotation group generates an order 3. We could just see that. We also talked about the alternating group when we were learning about S3. And in any Sn, there's the subgroup of even permutations, which this is, because it's generated by a pair of non-trivial transpositions. And so once you have if you're looking at the group of even permutations, that's exactly half of them. And so it's index 2, and therefore normal. And so again, we would get the conclusion. All right, and that's basically everything that I can think of to say about S3. A couple different kind of points of view there. Let's at least get started on D4 and see how far we get. So with D4, we want to use the same strategy, right? We want to know what are the kinds of groups that we can come up with, what are all the subgroups that we can think of, and which of them are normal. And even though D4 is not that much bigger of a group, only being 8 elements instead of 6 elements, it seems to me that there are quite a few more possibilities here. So let's try, and I'm going to do my best to be as thorough as possible, and I'm going to hope that I don't miss any. I don't know if it's clear at this point, but I try to work these out a little bit. Like I have a little bit of scratch paper where I try to work out some stuff. But basically, I try to share with you guys my stream of consciousness. You know, how does a mathematician really think about solving these problems? And so I'm hoping I didn't miss any. But let's take a look. So for the cyclic groups, again, we can think about the things that are generated by single elements. And so maybe it's wise to start by writing down all the elements. For the rotations, there are 4. Then we have the non-trivial reflection. And then that reflection composed with the rotations gives me other reflections. So here, these are 4 different kinds of rotations. These are 4 different kinds of reflections. And so a couple of things stand out to me. The first is that the group generated by R is the same as the group generated by R cubed. And inside of that is the group generated by R squared. These ones are order 4, and this one is order 2. In light of the fact that we just talked about, these are also normal because of the fact. But we can also see it above. So for example, any element of either of these is of the form r to the I for some I. And if I conjugate by any element, if I conjugate by any other r, like r to the j, I mean, this is clearly just going to cancel. All these things just commute. So there's nothing to check there. On the other hand, if I conjugate by an SR element, then I can try to bring the S's together. And so let's do that. Let's do SR to the I plus J. And then here, shoes and socks, this gets me R to the minus J. S inverse, which is also S, because every reflection is its own inverse. And now I have S R to the I, right? The J's up here cancel, S. And then lastly, the rule in this group is SR equals R inverse S. And so I can, by iterating this, I can bring all copies of R to the left and then get S squared. And it cancels and we get some multiple of R. And actually, if you think about this just a little bit harder, you can see that this one's also normal. And the calculation shows it. Because the only difference is elements of this group, well, this is just the group of E and R squared. And so in particular, I is either 0 or 2 here. I mean, it could be any even number. It's being taken mod 4, so it's equivalent to either 0 or 2. And what you see is the parity of I never changes. I just switches from positive to negative. And so if this was an even number before, it'll be an even number afterwards at the end of this calculation. And so I've shown that this element is also invariant under all conjugations. Or I should say this subgroup, but for E, it's trivial. Okay, this then brings us to the reflections. Can any of those cyclic groups be normal? Well, all of those are also abstractly isomorphic to a Z mod 2Z, but this time this is an index 4 subgroup, and so we have no reason to expect that these could be normal. And so we can kind of just check this. Let's say I take one of these guys. And let's try to check them all at once because that seems like it makes life easy. I have an SRI. And I'm going to conjugate this by something. And it seems to me like we can kind of do this all at once if I conjugate by, well, okay, we don't have to do it all at once. Let's just see what happens if I conjugate by an R to the J to get started. Then this gets me R to the J, S R to the I minus J. And now using the rule, I can switch these guys and get R to the minus J, R to the I minus J. And that brings me to SR I minus 2J. And the only way that, because this generates a group, Z mod 2Z, this has to either be E or itself. It's definitely not equal to E, because E is do nothing. This is some kind of reflection. And so can this be equal to itself? Well, that would mean that I is equal to I minus 2J, which only happens if J is 2. Because if J is 2, then this is 4, right? And we're looking at powers of rotations, which are mod 4. And so since it only happens if J equals 2, it doesn't happen in general. And that's really all that matters, to not be normal, right? If that there be some counterexample to conjugation sending you back into the same subgroup. And so none of these guys are normal, right? The I here is completely irrelevant. It just cancels from this equation. All of them are not normal. Okay, that handles the cyclic groups. Now we have to think about the two generator groups. And of course, we know that R and S generate the whole group, so we don't have to worry about that. And we've also looked at the groups that contain just the rotation. Sorry, I lost my train of thought there for a second. I was like, what am I trying to show again? Oh yeah. So we know that we want to be looking at groups that consist of some kind of rotation and some kind of reflection element. But if it contains, maybe this belongs written on the board, groups of the form R, S, R to the I. So some rotation, sorry, the order 1 rotation and some reflection, as well as the backwards rotation. these are always the full group. And the reason is because these just represent going clockwise or counterclockwise. It doesn't matter where you start from. And we originally defined in our first setup of the dihedral group that S would be the reflection through the vertical line. But that's a relic of how you draw the picture, right? I could like take my picture and turn it and then make whatever reflection I want the vertical reflection. This R will be some different R now, but it doesn't matter. In any case, you're always getting everything. If that seems a little bit abstract, maybe a direct way of seeing it is that by combining powers of R with this element, I can eventually make the R go away. And then I'll have either R or R cubed, and then the main reflection. I've got the full group. And so what this means is the groups that we want to be looking at are groups that use R squared and some reflection. And so I think, and I've got to scribble down on my notes here, that there are only two of these things. We have R squared, and let's see, sorry, I'm looking over my notes. It's got to be R squared and S, or R squared and RS. And the reason is because the others can always be obtained from one of these by combining with what we have. So for example, if I try R squared and R squared S, I could just combine R squared and R squared S to cancel the R squared. That would get me back to this one. Or if I had R cubed S, combining with R squared would get me back to this guy. And so we have these two possibilities, and we can write down what the elements of these groups are. We have E, R squared S, and R squared S. And those are the only elements in this group, because the other way of multiplying them would be SR squared, which would get you the same thing as R to the minus 2S. But since R to the 4 equals E, R squared equals R to the minus 2. And so these elements commute. That means this group is abstractly isomorphic to what we call the Klein 4 group, or Z2 times Z2. Very helpful. And this one has E R squared RS. And I guess we can multiply these together and get R cubed S. And I'm actually wondering if this, like, if I can simplify this, because this is not evidently the same thing as one of these guys. Maybe this is actually the full group. Let's check. So, oh wait, how could it be the full group? It can't be. It has to be a distinct element, because there's no simplification that I can do. So this is what we got. We can check if we're really unconvinced this is the full group by continuing to multiply some of these together. Like I could try multiplying RS by R cubed S and see what I get. If I do that, I could switch them like so. And then I get S R squared S, or R to the minus 2 S squared. S squared cancels, and R to the minus 2 is the same as R to the plus 2. So we would land back over there. Okay, hopefully this convinces you. All right, at this point now, this video is almost 20 minutes long. So it is, I think it's more than time to call it. So here's what I'll say. Because D4 has order 8, and each of these groups has order 4, we can apply the fact from above. And that allows me to cheat a little bit and finish this off before this video becomes any longer than it has to be, to see that because these are index 2, right, 8 divided by 4 is 2, they're normal. But I think it's worthwhile for you guys to try to just check that if I conjugate the elements of these groups by elements that are not in these groups, that I genuinely do still always get one of the elements in each group. This is a little bit laborious, but it's really not that bad, because once you've done it for R, you see how it works with R. It's the same for R cubed. And similarly with SR and SR cubed. And so there's a little bit of calculation to do here, but not so much that you couldn't finish it in another, minute or two of sitting.